get you all bored and maybe just give you the first thing, the cherry of the cake first. We can have it. And first of all, I want to acknowledge all my collaborators and also all the support that we have had from Randy and Marcia, basically when we tried to implement all these Businesque, basically Diego really went and dig into that part. And I'm gonna try to walk you through what the observations were. And the observations are clearly, like you can see on this simulation, is the simulation resulting from GeoClaw with some dispersive on it. So it has some Businesque on it. And it goes on a slow motion. Well, sorry. Well, don't worry, like it went on a slow motion, and what it does is that the SWOT goes so fast that it can really get you some idea of the snapshot that we have. So we are gonna try to walk here like through what I think SWOT is first, just to give you an idea for those that are not familiar with. It's a relatively new satellite, and we as oceanographers, we have been using it quite often for internal waves, for eddies, for any other thing. And it's just remarkable what the capacity of these satellite tracks have. And for now, was launched at the end of 2022. And it looks a little bit like this. It's the easiest way to relate to it is to look at bathymetry. If you were thinking on bathymetry from single beam versus bathymetry with multi-beam, that's basically what we have with SWOT. We used to have like a nadir, like an altimeter in the center that will just go. Let's see if I could have a pointer here. Laser pointer here, yeah. So we used to have this like altimeter that was just at the center, and now we have these two SWOTs on the side by side that depending which latitude you are at, it could be like 10 kilometers or 60 kilometers, and it goes really fast. So in about 20 seconds, you can have a snapshot of 150 by 120 kilometers, depending the area that you are studying. But it has a downside now. That is that it will come back to that orbit every 21 days. But because it's on a polar orbit, and this time was very fortunate that Kamchatka happened at very high latitudes, so then the orbits were repeated more often next to one another. And the orbits repeat every 21 days. If you ever were farming chicken, this is the time that a chicken takes to hatch. This is like every chicken hatching is a new sort of SWOT track that will come to the same place. So given that, like just a few examples of how it looks from SWOT, things that are interesting in the surface of the ocean. This is one of the machines that makes more internal waves in the ocean, in the Indian Ocean. And internal waves are these type of very dispersive waves that you can see. You can see here, like in this sort of SWOT track. This is sort of the SWOT track that we are using. For example, you can see very nicely these waves, but if you go in the super high resolution, you can even see the surface waves, like the swell. You can go all the way to that resolution to look into that. So that's why I think the observation that we had from the dispersion behind Kamchatka was really clear. And there's another idea, like what we had before on altimeter are those big squares, and what we have now with altimeter are those tracks that have it's like having a new pair of glasses. Just suddenly we are seeing things that we would have not seen before. And was this the first sort of satellite sort of observations from tsunamis? It is not the first one. Like Sumatra in 2004, there were two satellites that were able to observe. This is just an example of this very nice paper that showed the first really high resolution sort of satellite that went past. This is one simulation, but it sort of compares the simulation with just one equivalent, the altimeter that SWOT has in the center. That would be the equivalent that they were able to match here. And also another satellite did it. And on other successful observations, we have like Chile 2010, Jason 1 and 2 were able to observe that. Tohoku was also observable in few satellites, and Tonga was also observable. Tonga was 2022. If Tonga or SWOT would have been earlier, then we would have had one of the amazing observations. But SWOT was launched in 2022, and by that time it went on a CalVal period, so we were not. And this one, Kamchatka, was not actually the first tsunami that was observed with SWOT. The first one is this one, that is the Loyalty Islands. This paper is I think right now it should be published by Roger et al. And you can really see here, like there's the tsunami model, and then what you see is the SWOT track, and the next image is actually the observation of the tsunami with the SWOT. And you can see that is the leading wave, and then there's a lot of waves that they will feel really the characteristics that Marcia was mentioning, all the dispersive characteristics of this. But the shallow water equations were not able to reproduce that. Like this is the model that they were using in this paper, and this is the time series of, well, no, it's a long track type of section for the wave height model by the model is in red, and the observation just if you extract one line of that, it's the black lines that are behind here. And one thing that is important to notice is that if you actually compute the potential energy that comes behind the wave, that comes along with the tsunami, it's a lot more. You will still be missing some of that energy that will be eventually delivered into the coastline. So in terms of what we are going to see, it's important. Another one that was observable by SWOT was the Dixon Fjord. This is not really observing the tsunami, but they use the super high resolution to observe that sloshing, that the non-earthquake triggered tsunami happened in the Dixon Fjord in Greenland. And what SWOT was able to observe is what we have in the middle panel, that is the high state and the low state of the resonance. So there was this resonance that stayed there for what is like 9 days that remained there. I remember I tried to model this one with GeoClaw, and none of the waves will remain for longer time than 2 or 3 days or something like that. With the version that I used, I think probably one will use, and I don't know, that's probably something to discuss. If one will use dispersive models, will the waves will stay longer or the sloshing will remain there? That would be quite an interesting test for that, like the temporal durability of that. And then, well, how do we get into this one? Well, immediately after Kamchatka earthquake, I was already asleep. My wife woke me up, and he's like, hey, there's a tsunami. So I went ahead and started with Diego chatting, and Diego Melgar, and we started chatting, and we produced one of the first simulations, put it on Blue Sky. And by that time, I already had like one of my postdocs was working a lot with tsunami, and another team from France, from the European agency, they contacted us. They downloaded the Blue Sky sort of simulation, and they overlay on that the SWOT tracks at the time that they thought it was about the same time. And remarkably, like that simulation that was very simple with a slab model based on the characteristics from USGS was able to match it not too badly. So the track that they put there, and we decided, okay, I think it's worth to start making some progress on this modeling. And let's go ahead and try to match first the DART stations. And then we started having issues with DART. So DART, we started comparing, like here are 3 different DART stations. This is the time series of them. This is time after the earthquake. And the DART stations are in black. I know I have a lot of colors on this plot, but one of them is the 2419, which is like here in the sort of southwest. And that one had like the wave came earlier compared to the model, the USGS sleep distribution. And then the next one, like in the one in the middle, it was relatively okay. But the one that was further to the southeast of it had not a delay, but I had an earlier arrival compared to the DART. And the first thing that we thought is like, oh, maybe there's something wrong with the DART stations, similar to what we were seeing in the presentation before. Like there's a shift in the DARTs. So we had that shift done. And then that was the first problem, that we had to be able to compare the simulations that we had. And then, but definitely SWOT was able to help us to do just visually, like with the numerical model, we could see that it was not arriving at those times in few locations, even further downstream. But then what Diego did his inversion, that is like Gaussian inversion based on the DART gauges only. And he managed to fix that, like together, he made a hybrid version of a combination between the USGS sleep distribution, that you can see most of the sleep was close to the land, but the DART stations the inversion with the DART was able to pull more that slip distribution further away from the land. And few things to take into account is that basically there's no land around here. So some of the inversions that actually use some of the satellite interferometry or something, they will have nowhere to hold on them more material for the inversion. And then we went ahead with that new inversion that is the hybrid, and that's the green line that we are showing here. And we were able to actually fix the arrival times to the Dart station so we could move over, but we still had the problem with the dispersion. And we decided, are we really gonna go and do all the dispersion? I'm sorry for this part, but Diego called it like a nightmare. So it was very hard to work on that part. But Diego managed, like we were able to get that. And so here I'm going to explain how the dispersion at some point or to a relatively okay level was captured. So the first panel, the panel that says here B, is the SWOT track that we have. And basically what we have here is the dispersion that is observed by the satellite. On the second panel is only shallow water equations. We could see that in the north part, indeed, there are some dispersion that is generated by the bathymetry. So bathymetry does generate that. And then the shallow water equations can show that one, but nothing that is behind the main wave we can see in the shallow water equation part. So what we did for that one is like we actually did not reproduce the entire SWOT track, but we only reproduced half of the resolution of the SWOT track synthetically in GeoClaw. Basically, we did put 60,000, maybe it was not the best way to do it, but we put 60,000 synthetic tide gauges along the SWOT track and then analyzed that and eventually recreated this one to have like on the same time. But on the last panel, you can actually see that adding dispersion or the boosting X part, you can actually start seeing some of the dispersion that reproduces some of the dispersion that actually SWOT was able to see. Not all the dispersions was captured. And another important thing to notice is like then we start looking closer to the dispersion, like how important that is. So because SWOT has the possibility to have nadir, which is low resolution typical altimetry. On this sort of profile that I'm showing here, like it's a profile in the middle. So instead of it's on time, but time is moving here in this direction, but this is wave height, but it's along the path of the satellite. And the other two lines, the sort of green and orange, those are on the SWOT track, on the SWOT part. So that one has better resolution than the nadir. So even the nadir and previous satellites will have not catch all that richness of dispersions that we can see. And we're going to take a little zoom here, just at this particular region, and we can see all these waves that sort of like go up and down. So all these high frequency that we have behind the tsunami, the main trailing wave, and those we would have not been able to see with satellite. And we are trying to understand both the frequency content of these type of waves, characterize it with the field that is around it, and trying to also look at these type of characteristics in the previous tsunami and loyalty islands as well, just to see if there's any information that we could say. And actually, as part of the SWOT team is looking into potential errors, but I don't think that there are potential errors on their processing of that part. And finally, I just wanted to do this is the final model that we had. So this is basically the SWOT track. This is with dispersion. You can see slightly some of the dispersive behavior is behind the wave. And what we did here is you can imagine that you take a line of synthetic tide gauges along the SWOT track, which is here, and you just take it as a tide gauges to a pile up of the evolution of the tsunami as it comes in. And it was actually like a very lucky place for the tsunami to happen to show that dispersion is not generated by bathymetry, because here I'm showing, for example, along that path, the red line, the bathymetry that we have in all these basins that is being propagated with dispersion does not really have any features that you could think that is generating a dispersion. However, on the northeast part, that the bathymetry is a lot more complex, there's a lot of dispersion that is being generated there. Finally, the trailing wave is here, and we can see some of these giggles or like dispersion that we have behind generated by the model, because adding that dispersion really makes that, but it's free of bathymetry artifacts, I think. And that's what we were putting on this as a remark part. And just very quick to the summary, I think tsunamis are we believe, are no longer solitary waves as we thought for many, many years. We need to figure out a way to fix this part. It's both, as as it's been shown in the Loyalty Islands, small amplitude and large amplitude, they actually have some trailing dispersive-like waves structures behind. And all this basically is thanks to GeoClaw. So we have now a tool that actually makes this thing to happen. The good news is that we have more work to do, and it's probably important for forecasting. And one of the main things will be to estimate how much more potential energy is coming on these waves that are coming behind that. And also, finally, I want to thank the team. I think it was a very fortunate team. We had oceanographers, seismologists, and remote sensing experts all together engaging on this paper, and we were able to come up with what we believe is a nice story. And without that, thank you very much for your attention.